Vector addition and scalar multiplication component form. Right? These two operations don't have a lot to do with each other, but they are the two important operations on vectors, and honestly, they're not that difficult. Let's start with vector addition. In order to perform vector addition, we need two vectors. Let's call them u, which will have components of ux and uy, and v, which has components of vx and vy. All right, so x and y components of u and v are sensibly named with subscripts on the letters u and v. In order to add two vectors together, geometrically, we typically talk about this as a head-tail combination. So again, I'm going to stick with vectors in the first quadrant for my drawing. There's nothing special about vectors in the first quadrant. Everything works the same way. It's just a little bit easier to see what's happening. So the idea of vector addition is we draw the first vector u, and then we draw the second vector v, so that the tail of v is at the head of u. Right, so that gives us vectors u and v together. The sum, the result of adding these vectors, is a straight line vector that would get there in one shot without having to take the detour. And if you look at it, recognize that in the x direction, the total distance we went is ux and vx. In the y direction, the total distance we went is uy and vy. So to add two vectors, you add their x components and you add their y components. That's literally all there is to it. So if we have a couple of vectors of note, let's say we want to add 2, -4 plus -5, 7. We add the x components, 2 plus -5. We add the y components, -4 plus 7, and we end up at -3, +3 in this case. That's literally all there is to vector addition. On to scalar multiplication. This word scalar is quite possibly new to you. A scalar is the type of number that you are accustomed to seeing. Right? A real number in the context of vectors is called a scalar. But what I want you to really be thinking about is a scalar multiplication scales or changes the size of a vector. So if I have a vector and I like the direction that the vector is going, but I've decided that it hasn't gone far enough, I can multiply by a scale factor that is smaller than 1 and make a smaller vector instead. Or if I like the direction that this vector is going, but it hasn't gotten all the way to where I want it to go, I can multiply by a scale factor larger than 1 and get it to go further. Or if I think we went in completely the wrong direction. I can multiply by a negative scale factor and get it to flip around and go backwards. So that's the idea of a scalar multiplication. And in order to make sure that the direction stays the same, we need to increase x and y in proportion with each other. So if I have a vector, let's just stick with v with components of vx and vy, and I want to scale that vector by a factor of k. I write that as k times vector v, and I compute that by multiplying each of the components by that factor. Again, yes, that's all there is to scalar multiplication. So if I want to take 3 times the vector, say 5, -2, well then my x component is going to be 3 times 5, and my y component is going to be 3 times -2, which is 15, not 16, 15, -6. Right? That's literally all there is to scalar multiplication.